So let's begin our lecture video series on Chapter 2. And Chapter 2, the first half of it is all about the early discoveries in chemistry. So in the form of alchemical knowledge, or alchemists, chemistry has been around for hundreds of years. But the alchemists didn't really fully understand what was happening with the things that they were doing. They were in this constant quest to turn lead into gold, and they were making all kinds of actual discoveries along the way, but they didn't really understand very much as far as like deep knowledge about what was happening. So really this starts with the discovery of deeper knowledge actually starts in the late 1700s with Antoine Lavoisier. And Antoine Lavoisier is sort of loosely known as basically the father of modern chemistry. He was a wealthy French aristocrat, and in 1774, he started heating things in sealed glass vessels. Okay, so being wealthy, he had the means to purchase very sensitive balances and things, so he could take very careful measurements of all kinds of things. And so what he did was he would put, he's most famous for putting pieces of tin in these sealed glass vessels, and he's sealing it with atmospheric air. So he's mixing tin and air. Right, so nothing fancy so far, and then he heats it up. And what happens is, when he heats it up, he gets what's called a tin calx. Right, and essentially a calx is rust. Right, so basically he's rusting tin. So he knows he's making something is happening. He can tell. He can look at it. It's actually a different color, has different physical properties. And what he figured out was that the mass of the tin and air was the same as the mass of the tin calx and air. Okay, so prior to this, they were assuming that some of the air was going into the tin, and some of it was being lost. It was getting transformed into something else. And what Antoine Lavoisier's careful measurements showed was that there was no mass change because he was dealing with sealed containers. So nothing was different as far as the mass goes, even though he was making a new sort of component. And this led him to develop the law of conservation of mass. One of our more important laws in chemistry. And the simple idea with the law of conservation of mass is that the total mass of products is the same as the total mass of reactants. Okay, it's a pretty well-known thing these days, but in the late 1700s, this was to sort of codify this thing, and he had many measurements to back up his claims. And so, an interesting tidbit of chemistry history, right about the same time, there was a British chemist named Joseph Priestley. And Priestley did some studies that basically led him to the discovery of oxygen. So the idea that the air is actually made up of different components. Priestley tells Lavoisier about this discovery. Lavoisier starts doing his own experiments, gets a whole lot of data, actual numbers to back up these experiments, while Priestley is sort of tooling around with various physical properties of this discovery. Lavoisier publishes a paper and gets credit for the discovery of oxygen, even though Priestley actually was the first guy to do it. But Lavoisier was the first person to do experiments, take measurements, and publish a scientific paper on the subject, so he is credited with the discovery of oxygen. Later on, Priestley was added to that discovery, but for a long time, Lavoisier was the guy. Anyway, so to continue on, so the next guy we want to talk about is Joseph Prost. Joseph Prost. Or Proust, I'm not entirely sure. Joseph Prost and others, he wasn't the only one to come up with these ideas. From their work, we get the law of constant composition. Composition. Spelling is not my strong suit. I often have to sound things out. So, the law of constant composition says that all samples of a compound have the same composition. Right? The same composition, the same properties, and the same proportions of mass. Same proportions of mass of constituent elements. Proportions of, I should just write the words, mass of constituent elements. All right, and again, we're sort of laying the groundwork for a lot of the things that have caused chemistry to come along and to build and to discover. So with this idea of law of constant composition, you have every sample of, let's say, water is exactly 2 hydrogens and 1 oxygen. And we can talk about ratios of masses and percents of masses. Every single sample of carbon dioxide is 1 carbon and 2 oxygens. Every single sample of pure carbon is nothing but carbon. Okay, so constant composition, and it keeps constant the proportions of constituent elements. And so this is useful in determining the composition of compounds. So an example, you're going to find out that water is almost always my favorite example. Water is the best molecule in the universe. Fight me on it. Anyway, so H2O is 2 hydrogen atoms and 1 oxygen atom. Okay, and by mass, water is 11.19% hydrogen and 88.81% oxygen. Okay, so if I have, for example, 10 grams of water, then I can be certain that of those 10 grams, 1.119 grams are hydrogen, and 8.881 grams are oxygen. Let's say, for example, I didn't have such a nice round number. Let's say I had 27 grams of H2O. Then because of this law of constant composition and this relationship of proportions, I can confidently say that of those 27 grams, 3.021 grams are hydrogen and 23.979 grams are oxygen. Okay, so these two things, the law of conservation of mass and the law of constant composition, have been extremely useful in chemistry. It allows us to do a lot of what we do with stoichiometry, determining how much product and how much reactant and all kinds of things are directly related to these two laws. So the next big one that we want to talk about is Dalton. And to be honest, I forget Dalton's first name. It's not Timothy Dalton, the British actor, but Dalton and Dalton's atomic theory. And this is very, very important because it sort of lays some groundwork for a lot of things to come. So Dalton's atomic theory has three parts. So the first part is that chemicals, all chemicals, are made of atoms. And those atoms are neither created nor destroyed during chemical reactions. RxN stands for reaction, just a shorthand. Okay, so it's sort of the conservation of matter, right? So when we do chemical reactions, atoms get moved around, they can get swapped, they can get pushed off in another direction, they can anything like that, but they are never created or destroyed in chemical reactions. Second part, all atoms of an element are the same. Okay, and are different from every other element. Okay. In other words, the atoms of a particular element are unique. Okay, and all of the atoms of that element are the same to each other. The third part, in compounds, elements combine in whole number ratios. And this comes back to the law, and what this does is it sort of leads us to what's called the law of multiple proportions. Okay, building on the idea that atoms are indivisible, right? Atoms are the smallest piece of any particular thing. We can't have like 1.5 hydrogen atoms in a water molecule. It's always going to be 2 whole atoms of hydrogen and 1 whole atom of oxygen. So it has a whole number 2-to-1 ratio. Right? Now what the law of multiple proportions means is that I can have 2 atoms of hydrogen to 1 atom of oxygen, or 4 atoms of hydrogen to 2 atoms of oxygen. That ratio stays the same. It's still a 2-to-1 ratio, but I can multiply it, right? 4 atoms, 6 atoms, 8 atoms goes with 1 atom, 2 atoms, 3 atoms, okay? Or 4 atoms. So the proportions are maintained. So I'm going to go ahead and stop this video right here, and we'll pick up talking about the discovery of electrons.